Okay, hello everyone. Good morning to Asia and good evening to Americas. I'd like to welcome all of you to the APRU Multi-Hazard Lecture Series, Creating Resilient Society Against Multiple Hazards. This webinar series is organized by APRU Multi-Hazard Program and also the International Research Institute of Disaster Science, Reefs, Tohoku University in Japan. And I'm Takako Izumi, Associate Professor of Reefs, Tohoku University, and the Program Director of APRU Multi-Hazards Program. APRU is a network of 60 universities in the Pacific Rim and from 19 economies. And its international secretariat is based in Hong Kong. And you can receive more information about APRU from its website, including various programs and the network, which is Global Health and Sustainable City and Landscape, and also the Multi-Hazards Program. This lecture series consists of 2 sessions organized today and next week. And next week will be the 4th of August. And each session includes 2 lectures, and therefore we will have total 4 lectures in 2 sessions and within 2 weeks. And this lecture series aims to learn and discuss a social system required for a resilient society from different perspectives. Particularly, this series will focus on necessary approaches and mechanisms that can tackle multiple hazards through lectures on infrastructure resilience and resilience in cyber physical systems and science-based community resilience. And while you are listening to the presentations, I would like to encourage you to send us the questions using the chat function. And after each presentation, we will have a short Q&A session with the speaker. So I will pick up some of the questions from you and I will ask directly to the speakers. So now it is a great pleasure for me to introduce the first speaker today, Dr. Jonas Turing. He is the co-director of the Future Resilient System Programs. And Jonas completed his BSc degree in geography from the University of Zurich, Switzerland, and his master's degree in environmental impact assessment and management from the University of Manchester, UK. And he obtained his PhD degree from Kyoto University, Japan, and his research interest is to better understand human environmental processes in the context of disasters. And he enjoys engaging into the field work and has done so in various research projects in Ethiopia, Ghana, India, Japan, Malaysia, Vietnam, Singapore, and Switzerland. So his presentation topic is the overview of resilient systems. He will talk about what is resilience and what is required to achieve social and community resilience, and which stakeholders need to be involved in process and what are their roles in it, and how can these stakeholders collaborate in which areas. So I'm really looking forward to your presentation, Jonas, and thank you so much for your joining us, and floor is yours.
Thank you very much, Takako, for the introduction. Thank you all for joining this session. Let me share my screen. Can you see my slide? Okay, so thanks again for the introduction. Today, I would like to talk about resilience, and resilience is a topic which is very hot at the moment. We had a couple of disastrous events in China, in India, but also in Europe and in North America. So in the last few weeks, the world is experiencing a lot of different disasters, especially weather-related, climate-related hazards that have struck and that have caused impacts. So today I will talk a bit about this, but I will also touch a bit on the COVID aspect. Before we go deeper, I would like to ask the organizers to run a small poll so that we better see your background. Hopefully we can engage you in this lecture. So please have a few seconds to answer these questions. So do we have the results? Okay, this is fantastic. So 84% of the people use resilience as part of their academic work, and 50% roughly heard of the concept, and also roughly 50% they use it as part of their work. So that's really nice to know that so many of you actually are already familiar, so I can go quite quickly through the different topics of relevance. I would like to start the lecture with the outline. I will talk first about some of the extreme events that happened recently in North America and also in Europe, and then show a quick overview of the worldwide trend of disasters. Changes in global risk perception. I will go a bit more into the risk aspect before I actually move on to the question, what is resilience, talk about regime shifts, and then provide some examples how resilience was applied as part of my work, but also as part of the work that we do here at the Future Resilient Systems Program in Singapore. And then I will conclude and summarize what is a smart city and also a resilient system. I think many of you, or you may have heard about the recent event that we had in North America. There was a heat dome that happened at the end of June. And sorry about this. And what basically happened in this event was that there was a lot of wind flowing from east to west and preventing cold air to come from the North Pacific into the western part of the US. And because of the heat pressure area being sandwiched between two low pressure areas, there was quite a bit of heat concentrated over the area of Portland, Seattle, Vancouver area, and it created a so-called heat dome. And as a result of that, there was an anomaly of temperatures that were up to 15 degrees higher compared to other temperatures during the recent few years. So there was an excessive heat that was created within very short time, within very few days, temperatures went up. The impacts were more than 900 deaths. A lot of wildfires were created because it was very dry and hot. And the current estimation of damages are about 3 billion. During this event, a lot of people questioned, well, is this because of climate change? And the answer is no, it is not because of climate change, but it is an event which is extremely rare. And I will talk more about this. So there was a recent study developed by colleagues at ETH Zurich, and they actually estimated to what extent this event falls within other past events. And what we can see, it is a very, very strong outlier. So the anomaly of this heat wave over a period of 7 days was up to 11 degrees Celsius. And this was likely only possible or due to amplified climate change enforced warming. So usually we would have an anomaly which is maybe around 6 degrees Celsius compared to other years, but this time it went far beyond. And then the question often comes up, maybe you have heard about the black swan theory, maybe that you have extreme, unexpected, rare events, but this is not an event which cannot be explained. It is potentially a gray swan event, which is an event that cannot be based on historical data, because the historical trend, as you can see in this figure, would not suggest to have an extreme outlier. But if we look at the recent data and we look at the physical knowledge, then and combine it with historical data, then it is possible to have such an outlier. What we can learn from this event, that it's very likely that during the next few decades, these events become not anymore a 1 in a 1,000 year event, but might be 1 in a 40 or 1 in a 200 year event. So the probability of such events to occur is much higher. Then we had another event, the European floods, which was also a storm that was that brought heavy rain into different countries in Europe: France, Germany, Switzerland, Belgium, Holland. They were all affected by the same complex storm, and this storm brought a lot of rainfall. And in this case, again, it was major damages, more than 3 billion currently estimated, but only 200 people died. Again, it was an intense rainfall. It was forecasted in advance. It was largely a risk communication problem that not more people were evacuated. And therefore, it is neither a gray or a black swan event. We know that Europe is vulnerable to these kind of events, and we had the last big floods in 2005. which also brought heavy flooding. So this is another event that we can actually foresee and we should be able to manage. When we look at the number of disasters over the last couple of decades, then what we can see compared to 2000, we have about the same number of disasters in 2020. So there is not really an increase anymore since about 2 decades in the number of disasters. But I will later then talk more about the impacts and the potential damages from disasters, which is slightly increasing. But what I would like to highlight here in this slide is that since the early 90s, and thanks to the Yokohama strategy, efforts were made to actually protect assets, to protect communities, to protect the civil society from potential harm. And I think later then the Hyogo framework for action came, and also recently in 2015, the Sendai framework for disaster risk reduction. All these international policies help to develop structures, national structures, and platforms within each nations of the world to actually get better prepared to deal with extreme events. In another effort, which the World Economic Forum does quite a bit, is they ask their members whether they think how likely potential hazardous or potential risk would occur. And they also ask them what they see as a potential impact of these events. And what we can see here is climate action failure is a big thing, biodiversity loss, extreme weather. These are some of the impacts that are seen as very likely and also having a very high impact. When we look over the past 5 years or past 15 years, how this perception has changed, then what we can see is that due to the maybe recent pandemic, people see the likelihood of having pandemic much higher, so there might be a bit of a bias. But what we can also see is that the same happens for extreme weather. While in 2005, extreme weather was seen as likely, but not so likely. It is now seen as much more likely to occur in the future, and also possibly having a bit more impact. Another example which is interesting is that IT infrastructure breakdown. So what we had already in 2005 was that this is likely to occur, but the impact was seen as rather small. And what we can see now is that if the IT infrastructure would break down, the impact would be very large. And this can be explained due to the increasing interconnection and development of infrastructure all over the world. So a lot of activities that we are doing depend on a functioning cyber and physical system. And this is also a bit part of our lecture series that we will touch very much in the third lecture. So in order to understand resilience, I suggest to start first with understanding a bit of the key elements of risk. And therefore, I will start with a quick overview of the risk analysis framework. So typically, risk is defined as having hazard, exposure, and vulnerability. And this is usually put in an equation. There's a lot of sub-functions that play part of this equation. And so for hazard, we usually say it's a destructive physical phenomenon like an earthquake, a windstorm, a flood. Exposure we typically understand to be related to the location, attributes, and value of assets, and they might be affected by potential hazard. Vulnerability is about the likelihood that these assets will be damaged, destroyed, or affected when exposed to a hazard. Now, what is driving those different dimensions or factors of risk? One thing is obviously from a hazard perspective, we do have hazards that occur much more frequent, and those that occur less frequent may perhaps have also a higher magnitude. So we have an inverted shape of the curve. So impacts or like hazards that have a low magnitude may likely occur much more often. And this curve might be influenced or driven by potential climate change. So climate change may possibly change the number of high impact events, and maybe the magnitude of a flood may potentially increase due to climate change. When we look at the exposure, then we would like to see what kind of assets are exposed to a potential hazard. And in this case, I'm showing a map from Ho Chi Minh City where we have a flood model showing the areas and then the road network that might be potentially exposed to flooding. And this again is driven by urbanization. So if we have more urbanization, we also have more assets that are potentially exposed to a flood hazard. When it comes to vulnerability, we want to look at the possibility that there is potential damage that can occur. And this is dependent on whether we are obviously more exposed, but also whether, for example, the soil condition is good or bad, whether the houses are built in a good way. So this is all driven by factors that are related to how vulnerable we are and how likely our assets would be affected. What we can see is that the lower the flood level is, the less damage we have. The higher the flood level is, the more damage we have. And here is the critical point. Here, we need to understand the human environmental coupling. So if we have, for example, more urbanization taking place, which is the case in many parts of the world, especially in Asia and in Africa, we can expect, or what we are witnessing is that more and more assets are planned in hazardous area, and that creates a coupling. So basically our exposure increases, our vulnerability increases, and if on top of that hazards become more frequent and more intense in the future, we are very likely to be more at risk in the future. So then turning this into the connection between hazards and disasters, we need to look at what is the probability that a certain event causes a certain amount of loss. And here we have again the inverted shape of a curve. Basically an event like what happened in Singapore in April was an extreme, not extreme, sorry, it was a small rainfall event which could be absorbed by the existing storm water drainage system. And you can see here the transportation network is slightly disrupted, but is still working. So the losses were marginal, very, very low, but these kind of events occur very regularly. We had already quite many events like this in Singapore this year. And then in contrast, we do have a very extreme event, which has a very low probability. And this is like Hurricane Katrina in 2005. This was an event which is very rare to occur. But if it occurs, it has a very, very high impact. Now, when we look at I showed before the number of disasters, and now I would like to show you the number of impacts, like the economic damages that we witnessed over the last decade. Swiss Re provides us good data on what is actually the damage level and also how much of the damages are actually insured. And the blue line shows you a bit how much of the total damages from earthquakes or weather-related disasters is being protected. And what we can see is that there's always a very large fraction of potential damages that are not insured. And this is what we call as a protection gap. Let me continue. So we do see a trend that the insurance market can actually not cover all the potential damages. And this asks us for additional measures. And this is, in this context, we often say, well, we need to have more resilience. We need to increase our disaster risk reduction efforts. So this is what we need then to consider when we plan for protection or for DRR. This is something that we need to take into account. So from a risk horizon perspective, we need to think about what we can do. Insurance products focus more a bit on the short term, but cities, they need to look very much at the long term. 50 years is a typical planning horizon. And then the question is, can we predict how our cities, our regions will develop? How can we plan them in a way that we do not have more risk, that we do not have more unplanned development, that we take into account the capacities that the soils, for example, have? And given that climate change is accelerating over time, maybe even think about mitigating risk and maybe even trying to reduce our risk exposure. So this will be the challenge that needs to be taken into account when we think about managing risk. And again, I would like to complete this part by focusing on the uncertainty aspect. I showed you before this slide, but because of climate change, and because we don't know how people are developing, and because we don't know how assets are being developed in hazardous area, there's a lot of uncertainty. So we don't know whether this will increase, whether this will be stable, but it is possible that these changes in land use, as I call it, and especially urbanization, may potentially change the possibility to have hazardous disasters or like impactful disasters to occur. Traditionally, we have looked at disaster risk management to manage these disasters. And as I showed before, the pictures of Singapore, we can do that very well for a small impactful disaster, which doesn't create too much of damage. We can easily absorb it, we can respond, we can recover from it. But the more intense, the more severe the disasters the disaster become, the more difficult it is. And at this point, we need to look at efforts that are on top of the risk management and possibly look into the resilience aspect. So what is resilience? Resilience is, in this context, defined as the ability of a system, community, or society exposed to hazards to resist, absorb, accommodate, adapt to, transform, and recover from the effects of a hazard in a timely and efficient manner, and including through the preservation and restoration of its essential basic structures and functions through risk management. There are a lot of definitions that define resilience. This is just one, which is in the context of disaster. But it is important to understand that it is about the ability, and it is about the ability of a system and of a community to deal with this, which goes beyond how we can manage risk. And this is important and has become much more accepted over the last decades as a concept to be translated into the work in the fields of environment, in the fields of social science, but also especially in the fields of disaster sciences. So the background of resilience started already many centuries ago, but recently in the 70s, the focus was very much on ecological resilience, where we look at potential changes in populations and then see how they have an impact. Then over the last few years, socio-ecological resilience became very apparent. Basically, the question was, how can potential disturbances impact the ecology, how populations would change over time, and also how people can be part of this process. And then that's also where the community resilience became more pronounced. And there is one important contribution by Michel Bruno, where he provides sort of the technical basis for resilience assessments. And out of this work that started in the last couple of decades, a lot of publications now have emerged in different fields, whether it's on transportation, whether it's on critical infrastructure systems, but also on food systems, which I will also speak about, and organizational resilience. So there are a lot of sub-fields that are emerging, that are developing and using resilience as part of their work. We will see how it develops. At the moment, the trend is that a lot of publications come out on the topic of resilience. When we understand in our center, in the Future Resilient Systems Center, we typically define resilience as something that is potentially affected by uncertain, maybe ambiguous or unexpected shock, and the system may to some extent be able to absorb the shock, but then maybe have a reduced performance level for a certain period of time, and then depending on its capabilities, it is able to reconfigure, it is able to recover, ideally even adapt and learn from this event. In the worst case, it might be even collapsing, and that's not what we want to see, but this is what we need to consider also from a resilience perspective. And another point that is important in the concept, in the understanding of resilience, is to understand regime shifts. I mentioned before about ecological resilience that came in the 70s, and the work that has been developed in the last few years has actually looked at past events where there was a sort of a large, persistent, and usually unexpected change in ecosystems and socio-ecological systems. So this sudden change of conditions in the environment, in the ecology, was witnessed in the past, and in this case, for example, in the Sahara 5,000 to 6,000 years ago, suddenly there was a decline in terrigenous dust and vegetation cover, and this led to a collapse of the system and created the current desert. Another example is coral reefs. As you know, the oceans around the world are warming, which is putting those coral reefs at risk. And this is potentially having high impacts, because once the water is too warm, then the coral reefs die. And again, in return, it has impacts on the biodiversity and available resources for humans. So we would like to know, how strong can systems be? How strong can the ecology be? How strong can socio-ecological systems be to deal with potential disturbances? And that's where resilience comes into play. Going back to the critical infrastructure systems part, which is important in our program, I would like to highlight here one contribution from one of our postdocs, Minh. She has conceptualized resilience for infrastructure systems. And one key aspect is we need to understand the intrinsic capabilities. And I mentioned before, intrinsic capabilities are important because we need to anticipate, we need to be able to absorb a potential disturbance, we need to be able to recover and adapt. And this cannot only take place through external support. We also need to know how the systems themselves can actually manage potential disturbance. So there are different ways how we can look at it. There are different models that can be applied, and I will touch on some of them. One other aspect to consider is in infrastructure systems, which is very important, that a lot of systems are overlaid. So we have buildings, roads, we have power lines, telecommunication, water, canalization. We have a lot of networks or systems that are overlaid, that are in some ways interdependent to each other. And this is very important in the context of resilience, because it could be that a road gets disrupted and can have impacts on another system. So in this example, for example, there's a water pump that has a blackout, which then has impacts on maybe the power grid, but also on the water network, and maybe even on the provision of supplies to households. So one break of a potential component of a system would have impacts across the network and also among other networks. And this is something that needs to be analyzed in the context of dealing especially with infrastructure systems in the urban setting. And we have done some of the work related to this, and my colleague E will show you much more in the next lecture, but I just want to highlight on this point that it is important to use existing data and think about what is available to identify critical road links, in this case in Ho Chi Minh City, see how that connects to flood models and how urbanization and population density could have impacts on the provision of medical services and emergency response. So in this case, network analysis was applied and then visualized in a user-centric visualization tool, URscape, which was developed in our center. So E will talk more about this in the next hour. Another study that we did in our center was to look at modeling of recovery process. So based on different mathematical functions from the gamma family, it was possible to estimate parameters of recovery for the power supply of power utilities. And then it was applied for a case study that affected several power utility companies after Hurricane Sandy. And what you can see in the figure here is that a lot of power supply companies had a reduced area of customers that they could serve during a short period. But what we can see is that depending on how much they were affected, these power companies, they could actually supply more or less. And what we can see, especially in the parameter B, is that there is a lot of capabilities within the system to intrinsically recover and provide, again, services to their customers. So this is one approach to quantify resilience and especially quantify the recovery process. Another study which I was working on in Morocco was focusing much more on food systems. And in this case, the idea is to understand how within systems the potential dynamics perform. So we do have a lot of different feedback loops when it comes to the provision of, for example, tomato production in this case. So we know there is a demand for water to produce tomatoes. And if we have more water, we can actually produce more tomatoes. And then if we have more tomatoes, we can actually invest more. And so there are different impacts or different feedback loops that we can take into consideration. And when we then run a sensitivity analysis, we can actually see how sustainable we are in the context of groundwater depletion. Tomato production in Morocco is not so easy because Morocco has not much rainfall, and therefore it requires a lot of groundwater. So if there is excessive use of groundwater, it is likely that the groundwater depletes. And what we can show based on this model is that we can determine critical thresholds. In this case, we know if we continue at the current trend to consume water and do the intensive tomato production, then maybe in the next couple of years, there will be severe groundwater depletion unless we take measures to actually collect more water, ensure that we have less water that we need to produce tomatoes, then we can maybe manage this. So this is one approach to look at the intrinsic capabilities of a system. Another work that I was involved and we are looking at is more at the COVID aspect. Here again, we would like to understand how the COVID-19 had impacts on social networks, on social support, also on the social cohesion. And for this, we applied a survey in both countries, in Singapore and Switzerland, and we asked people whether they changed the social network, whether they actually provided more support to their neighbors, and also whether they actually trust their leaders, governments more. And what we can see from these results is that the social network and also social support didn't really change because people had to stay mostly at home. So social distancing actually resulted in very small uptake of support to neighbors, of families, and so on. And this is in contrast to maybe flood events, where we see a lot of community engagement in managing the disaster. And what we can also see that in both countries, actually, people very well responded to the governmental measures that were imposed in the early part of the pandemic during March, April, May 2020. So people actually felt that was pretty good. What we then can find as a result of these studies that collective action is not so critical during a pandemic. We also felt that it is important to monitor the changes over time. So we are running currently a second survey to see how it changes over time. And also we feel that online tools, online technology helps us to maybe build some of the social capital via online interactions, Zoom, for example, but also WhatsApp or other social media exist now to actually help people to manage this pandemic. And this should also be considered when we talk about social capital. In another study, which goes more into the interconnection between people and power systems, we had colleagues in our program who did a time series analysis of residential electricity consumption among households in Singapore. So we could get smart meter data, see how much people consume, and then put that into connection of how it is during the day. So you can see on the left figure, you can see that towards the evening, people consume much more electricity. And when you look at the figures B and C, you can see that based on having new cases and new people or more people recovering from the COVID, we actually see also that there is an impact on producing more electricity. So there is somewhat a correlation between the number of cases of COVID and how people consume electricity, and they consume more electricity when there are more cases. So there is some sort of causality. There is also a proactive response, in this case of Singaporeans, people living in Singapore, to manage to proactively deal with the circuit breaker that was imposed between April and May 2020. So this is another study trying to look at how people behave during the pandemic, how they change their electricity consumption. And it shows very strongly that there is an impact between what people do, individuals, and also what the power system needs to supply. So if we have a sudden increase of power in the evening, and we can see the same in Singapore during the evening when it comes to the internet usage, the internet then becomes a bit slower, and that needs to be taken into account when we develop robust internet, or in this case, in this particular study, power systems. Going back to the urbanization, going back to the exposure, and going back to the need to make cities more resilient, I would like to show you this project, which was developed by colleagues from the Cooling Singapore team in our center. And what they do is they use a weather research and forecasting model to visualize the urban heat island effect in Singapore. And what you can see is that during the afternoon, in this case, the urban heat island effect starts to build up, and it becomes much stronger than towards the evening. That means the temperature between the rural area and the city area becomes much more different, and especially during the evening around 11 o'clock or midnight, the heat island effect becomes very strong. Why do I show this in the context of resilience? Eventually, we need to think about how do we build resilience in cities, particularly cities are at risk, and the urban heat island effect is just another driver that needs to be taken into account into the numerous factors that need to be considered when we want to build resilience in cities. And what you can see in this case is that the temperature increase is very considerable. I mean, we are talking in Singapore has about an average yearly temperature of around 28 degrees or so. And here we are showing additional heat up to 7 degrees Celsius. So if we have urban heat island effect and on top of that climate change, then we are dealing with a situation that can become potentially a hazardous or even more hazardous situation. And eventually Singapore may even become much less habitable, may have impact on the livability quality, well-being will be at risk. And this needs to be taken into account when we plan for cities. So that brings me to the last three slides. And I would like to conclude this part by highlighting that we are pushing efforts to develop smart cities around the world. This has taken up a lot of ground. Recently, many cities around the world would like to become more smart. They would like to integrate more the physical systems with potential cyber systems. There is a lot of possibility to collect data through sensors and at different scales, at different component levels. We can collect data through our smartphones. We can have all sorts of weather sensors installed. We can have vibration sensors installed on cars, on vehicles, and so on. So we are now in a situation to collect a lot of data, and this data could help us to better understand how systems, how individuals, how systems, as I said, can perform under disruptions and also during normal times. We may also look at thinking about how we optimize the resources. How do we deal with the available land space that we have? I mentioned before the heat island effect. In order to reduce the heat island effect, we must have more green space. So when we plan for cities, we may take this as well into account. We need water supply, we need power supply, we need to have production of renewable energies and so on. So there is a lot of land space that is required next to the goals of building more houses or accommodate more people in our cities to deal with urbanization. So I come to the conclusion. We need to look at extreme events more and more because they are likely to become more frequent due to human-induced climate change. Urbanization is likely leading to a coupling of hazard, exposure, and vulnerability. So we need to think about how we can better manage urbanization to avoid negative consequences and reduce and make sure we do not have too much risk exposure. Insurance may help to some extent, but we still need to actually plan cities that they can actually reduce their exposure and can better manage complex crises. So risk management needs to be complemented with resilience management to better deal with unexpected, rare, and high impact events. Currently, the focus in resilience research is on understanding the intrinsic capabilities of systems and how they deal with potential disturbances. Finally, digitalization allows individuals to be directly connected to physical systems, and there is enormous research opportunities that are around using AI and machine learning, just to name a few of the techniques to analyze this big data and to better understand the resilience of social technical systems. So finally, if you are interested more about what we are doing at the Future Resilient Systems program at the Singapore ETH Center, here you have an overview of our program structure, and what is our vision is to develop and deliver novel solutions for resilience management through engineering, design, and social research. And the focus is very much to look at the cyber-physical system connection, look at how urbanization has impacts on cities in the high density urban systems cluster, and then very much look at how individuals, how social groups are connected and to urban infrastructure systems and how they actually shape the resilience of cities. Now this brings me to the end of this lecture. I'm happy to answer any question, and I will hand over back to the organizers. Thank you.
Okay, thank you so much, Jonas, for your wonderful presentation. It's very informative, and we learned about resilience as a system quite a lot. So we have some questions. First of all, can we consider resilience as the flip side of the vulnerability?
Sorry, do you mind to repeat again?
Yeah. Can we consider resilience as the flip side of the vulnerability?
No, I cannot agree to that. I think vulnerability talks about the likelihood that potential assets are affected. So it is talking about how these assets are basically at risk, but yeah, exposure and resilience is looking much more at how systems have intrinsic capabilities to deal with potential hazards.
Okay, so the next question is, could you provide an example on how the current systems can be tweaked to make more resilient, as building systems ground up may not be an option in most cases?
Thank you for this question. What we are doing typically is we try to analyze what the systems can do. So there is a thorough analysis of what the system can do, where are the weaknesses in the current system, and if you detect this, and it's a typical problem-solving approach, if you detect the weaknesses, you try to address them. But at the same time, we need to understand, when we do understand the weaknesses, we need to think about the trade-offs. So relying on a system that is not reliable, that is not providing resilience to the system, might be potentially dangerous. So we need to think whether we try to reduce its usage in the short or maybe medium term and replace it with a better, more resilient system. But I think we need to look at the individual case. So now it's a bit abstract to answer this question. So I will need to have a specific example where it is.
Okay, another question is, what should be done in developing countries to boost infrastructure resilience?
I think we should start with a mapping. We should think about what are all the infrastructure assets that we have. For example, what we have been also doing is we have OSM data, for example. So the very, very first step is just to map out which assets or which infrastructure systems we should look at. So yes, we do have roads, we do have power plants, we do have airports, we do have hospitals, police stations, schools. All these assets we may possibly first map out and then potentially in a very first step do a qualitative analysis to see is there a concentration of some of these assets, and maybe try then to identify those potential concentration and potential risk that is linked to that. And then, as I mentioned before, try to have a comprehensive assessment to see how these different infrastructure systems would be managing potential disturbances.
Okay, so our next question. Is there a scoring system to measure resilience across a number of variables of, say, a city? Do you see value in this?
There is, yes, I think there are some international organizations that develop some of these resilience scoring systems. Personally, I don't think this is valuable, because we need to really look at the individual case, and we need to look at the we need to think about what we put into the index. Usually these scoring systems, they are based on an index, and what I can see, for example, recently we had a COVID-19 resilience index, which was developed I think by Bloomberg, if I'm correct. And what we can see is that some of the nations or some of the cities are very resilient, but in reality, they just do have a lot of money. And so money is the driving factor whether they are resilient. And I think in this case also we need to shed more light on the intrinsic capabilities to see actually what can the system provide given the context. So if you have a power plant, if you have a road network which is super crowded, you may know that maybe it is not that resilient if there is a disturbance, but maybe it is still quite adequate for the given context. Whereas in a city like Singapore, if there is a little bit of rain and the road network easily gets disrupted, then the damages are very high. So we need to think about what is our goal when we do these kind of indexes or scorings.
Okay, yeah, thank you. I think we are getting more and more questions, and I hope it is okay to continue asking more questions. And of course, I'm sure many people are interested in the concept of resilience itself and how to measure it and etc. Okay, so the next question also, I think it's related to that, the former question. And regarding the concept of resilience in science, has there been parameters for resilience developed in transportation, social, technical, organizational, and resilience in general?
I think I would like to answer it in this way. Yes, parameters are or have been developed, but they are currently in development. I think this is a topic which also my colleague later will address, but I would say something that is now becoming more and more important. In the past, this was less the case, but now this is currently the research focus. Basically estimate the parameters for different infrastructure systems.
Okay, so so for building a resilient community, how will you describe the necessity of social cohesion during any emergency or pandemic situation? And in the digitalized era, where people are disconnected physically, what steps can be more approachable to build their connection?
Build the connection.
Thank you for the question. I think yes, the necessity for social cohesion is very important. It is impossible to manage a pandemic without the support and the cooperation of the people. We see that very, very strongly in Singapore. Singapore is basically, how to put it, in a lockdown since about 1.5 years. We can go out of the country, but we if we want to come back to Singapore, we have to go into quarantine. So people are basically sitting in this country, which is very small, 720 square kilometers. 5 to 6 million people are living concentrated on this small surface. They need to cooperate with what the government says. So it is super important that people are willing to follow that. And in a digitalized era where people are disconnected physically, I think the steps are really to work more with the available tools. So we have phones, we do have media that allows us to reach people. This is working right now. We possibly have to intensify those efforts. The question is whether we trust the information that is sent via these tools. But it is possible to do that. We are currently talking about building online social capital. So this would be a new research area that is maybe emerging now gradually.
Okay. So next question is, which is more effective in integrating resilience into the development projects of the private sectors, implementing stricter regulations or providing incentives?
I think this is always a bit of a question of what is the funding situation. And I think when we say about integrating resilience into the development projects of the private sector typically has an own interest to develop projects that are resilient. I think what we see, especially with the World Bank, is that resilience becomes now a more important part of the development projects, and also funding that is being dispersed or allocated needs to have a resilience component in it. And the World Bank is currently intensifying its efforts to do more resilience related development projects. So the projects need to be more resilient. Now the next question is about a policy aspect, whether we should have more regulations or incentives. Typically, I mean, the pragmatic, safe answer is to say we should have both. I would say when it comes to buildings, yes, you should have clear regulations on the building height, on the building exposure and all this. When we talk about incentives, for example, in Singapore, you don't need incentives to encourage people to do the vaccine, because people want to soon go out of the country and they know that only with a vaccine they can actually leave the country. So there is enough incentive provided through the peer pressure, and that goes back to the social network and social cohesion, how much people actually are cooperating with each other. So incentives can work. We know economic models show us that incentives can work for some of the cases, but in some cases we need to have a regulation. So it needs to be a mix depending on the sector that we target.
Okay, thank you. And I'm sure you are currently conducting the program on this resilient system. So of course, your program's goal is to implement in reality or creating this kind of society in the future. Is that correct?
This is correct. Like there are other programs also around in the world that look at resilience, very specifically at resilience. In our center, the focus is a bit more on the infrastructure or social technical connection. And we would like to come up with more models, come up with what you just asked before about parameters. Would like to be better able to tell people how can we develop resilience in cities or in what we call high density urban systems, and ideally develop a system of systems understanding. So basically understand how overlaid interdependent systems relate to each other, how people shape and control these systems, and maybe also how we can make use more of new available digital tools like phones and so on. So there is a lot of development in the next decade that will shape our relationship and our ability to live in high density urban areas, and also how we are connected to the different physical, environmental and social systems.
Okay, yes, and of course to implement this program, and of course it's so many issues are interrelated. So there are so many stakeholders have to get involved in it, and government and academia like yourself, and also private sector and local government. So how do you think how can they work together to achieve this goal?
I think what we saw in the last decades is that the Hyogo framework for action and also the Sendai framework for disaster risk reduction have helped quite a bit national governments to establish the structures. We know very much from managing disasters, managing disruptions, that we need to have a concerted effort between the private sector, the society, the government, the policymakers, and so on, to manage this potential disturbance. And the COVID-19 pandemic has once again shown how important it is that these different players, these different stakeholders, actually work together and have a concerted effort to avoid having inefficiencies, to make sure that the costs can be kept under control, although this pandemic is very expensive. But we need to have the different players on board. And I think that what the UN framework does is really helping to keep a sort of a structure in place to allow governments at the local, regional, and national level to develop the sound structures, governance structures, but also incentives and even regulations, what we mentioned before, to actually develop resilience in their cities or systems.
Okay, thank you so much, Jonas. And I'm really looking forward to hearing more about the results of your program and also how it goes in Singapore. And once again, thank you so much for joining us today. We received so many questions, and I'm sorry we could not ask all the questions, but it's a really great session. Thank you so much, Jonas.
Thank you very much, and thank you all. And if you have interest for more questions to be answered, please write me an email, and I'm happy to answer them.
Okay, great. Thank you.
Thank you.
Okay, so we will have 5 minutes a break. Then we will start the next session by Dr. Wan from 12:05. Sorry, it's in Japan time, 12:05, but in 5 minutes, and we will start the next session. So please come back in 5 minutes. Thank you. Hello, everyone. Welcome back to the session 1. So now I'd like to invite the next speaker, Dr. Yi Wan, and she is currently a postdoctoral researcher in the Future Resilient Systems program at the Singapore EGH Center. And she's a colleague of Dr. Jonas Turing, who is the former speaker. And her research is centered on transportation network design with a focus on environmental sustainability. With her background in transportation and operational research, her current research addresses the resilience in transportation systems and its interdependency with other urban critical infrastructures. Since July 2019, she is a part of research collaboration with the World Bank and Ho Chi Minh City, demonstrating the significance of incorporating resilience, thinking into public infrastructure planning. So her topic of the presentation is infrastructure systems resilience. So she will talk about what is infrastructure system resilience and what are the relevant dimensions and its significance to hazards, and why is it resilience important? What are the complex interdependencies within infrastructure systems? What is necessary to achieve resilient infrastructure? So thank you so much, Dr. Wan, to joining us today, and I'm really looking forward to your presentation. The floor is yours.
Thank you, Professor Izumi, for the kind introduction. Let me share my presentation. Can you see my screen? Okay, I think I'll start. Thank you very much for joining today's seminar. I'm Yi, the postdoc researcher from Future Resilient Systems. So today I'll be jointly with Jonas to share what we have done from our Future Resilient Systems. From my field, especially from the critical infrastructure systems. So today I will be firstly talking about what the critical infrastructure system resilience is, the definitions, the dimensions, and also the complex interdependencies among them. And also then we will move on to my field of research, more on the transportation system, where firstly I will give you an overlook of the global natural disaster risks that the transportation systems are exposed. And also I'll be showcasing 2 use cases that we have carried out during the past year with a collaboration from the World Bank. One is focusing on the BRT project in Ho Chi Minh City, and the other one is focusing more on the societal aspect of transportation support for the emergency services, and then followed up by the summary. So first, since we talk about critical infrastructure all the time, what are they? The definition of critical infrastructure is as follows. So we are referring to the assets, systems, and also networks that provide essential services for the security of a nation and its economic prosperity, as well as the health and safety of the citizens. So usually these essential services, they are composed, require a complete critical infrastructure system from 3 aspects. So the first one is the one or multiple physical assets connected in a network. For example, the roads in the transportation system or the power plants in the power system. And also there is a great aspect of the inputs. So we're talking about the raw materials flowing in the logistic networks, the fuel and electricity in the energy systems. And last but not least is the people. At least for now, the world we're living in, we still need human in the system for operation, for management and such. So there are 6 sectors widely classified as being critical. They are the water and sanitation, the energy and the transportation, the finance, the health, and the information and communication technologies. Some countries also include sectors such as education and critical economic and manufacturing with their definition as well. So this varies from countries to countries as well. So these systems, as we can see, they constitute the backbone of more than interconnected societies. They enable the commerce, the movement of people, goods, and information, and facilitates the society's daily activities. So not only the critical infrastructure are vital, the services they're providing are also essential, as I just mentioned. And here is a technical report from the World Bank Group under the disaster risk financing. They pinpointed that the disruption to critical infrastructures can emerge not just from physical damages, but also the disruptions to services that involve the people, inputs, and even shocks to demand. So we can see that the direct damages from disaster to the power and generation and transport infrastructure, they are estimated as 18 billion a year in the emerging and developing countries, but the estimated cost of the associated disruption to the services they provide ranges up to 647 billion. This is almost as 20 times larger as the direct cost from the physical systems. So for this reason, the critical infrastructure resilience is vital because it is not about protecting critical infrastructure, the assets only, but also underpinning the services they provide. So I believe everyone would probably still remember earlier this year when the Texans suffered from the unprecedented, unplanned power outages in February as a result of the deadly winter storm and record low temperatures in Texas. 4.5 million people were cut off from power. But is that it only? Of course not. The disruptions to critical infrastructure systems, such as this power system, frequently cause major social and economic loss, both directly and through failures in one system leading to another. So let's use this case to illustrate how failures can possibly propagate and amplify within and across complex systems. So I have gathered several pieces of news regarding this outage and linked them back to the critical infrastructure system we just identified. So first, of course, the direct heat from the winter storm was onto the energy system. Then there's this massive electricity generation failure. 4.5 million homes and businesses were left without power. A second direct hit from the winter storm was onto the water system. So the water service was also disrupted for more than 12 million people due to the pipes freezing and bursting because of the record low temperature. And another direct hit from this winter storm was onto the transport sector, because due to the extremely bad weather, a lot of intermodal freight network was shut down. And also even the service was on, the train length was significantly reduced for safety reasons. So the throughput of the transportation system was significantly reduced. And now let's look at what else happened in between the systems and also beyond them. So there is this piece of news that indicating because of the power lost and the water treatment facility, this forced a city-wide boil water notice to be issued. As we all know that the hygiene of water is really crucial after big disasters for the health of the citizens. And not only this, but the non-urgent surgeries as well as a lot of patients were also transferred from hospital to hospital because of the water shortage, as well as the low water pressure that causing problems for the heating system in the hospital. So this links between energy system towards water and then further towards down to the health sector. And also, there is the impact from energy system to transport and further to manufacturing. How did this happen? Because the power outage have also impacted the rail traffic, which is crucial for many supply chains. And this, of course, led to impacts to the manufacturing, to the warehousing, and also the store operations. And this will brought definitely a cut down in the revenue in a lot of sectors. And surprisingly, it even impacted the semiconductor market, because given the special location of Austin, there are a lot of semiconductor plants clustered around it, and they are shutting down, further disrupted the supply chain of this product, which has already been falling short of the customer needs. So this is totally a complex, non-linear failure from one sector to another because of something concurrent happening that we could probably never foresee. And last but not least, the energy system failure also caused chaos into the financial sector, where the electricity prices on the state's wholesale market soared by 47 billion, and some energy firms made billions in profits, while the others went bankrupt, sadly. So as we can see, all these interdependencies and their many dynamic and multidimensional parts necessitate a system approach in order to fully understand and assess where the vulnerabilities lie. It might not only lie within one single sector or system, but probably on the linkage or on the effect they have onto each other. Then we can identify where the resilience can be further improved in a holistic point of view. So we've already mentioned this word resilience for quite a few times. And what does it mean in the context of critical infrastructure? So here I'll introduce you this famous resilience triangle proposed by Brunel in 2003. So this was the first time that this concept was applied in the critical infrastructure context. More precisely, it was about seismic. So this provides the academic or the word with the technical base of resilience assessment. So we can see that the understanding is probably that there is this process of observe the system undergoes in response to a disruption and then quantified in terms of a measure of system performance, and then its response to the disruption changing along the time after an event. So we can clearly see there is a drawdown always because of the loss of system performance, and then followed by possibly a bounce back, which is reflecting the recovery behavior of the system. But this diagram here, so the definition of the resilience is in general is describing the ability of a system to reduce the chance of shocks and also observe if the shocks occurs, as well as recover quickly after a shock. So it's threefold and is expanding along the time dimension, as we can tell. But this diagram is also a bit simplistic, that it does not show the impacts from gradual change. You can see the drop here is pretty sharp, and also nor does it demonstrate adaptation, because it goes back ideally as how it performed as before. So more recent development on this field has classified 4 typical recovery behaviors to capture the key outcomes and bounding cases. So now we can see there are several curves to reflect the recovery behavior and also reflecting different level of losses. For example, the robust one. So this one indicates that the system returns to its initial state before the disruption event. And what's better is this called adapted behavior. So which means the system compensates the loss in performance and even reaches an improved state compared to the initial state. So this reflects that there is not just a simple recovery, but a reconfiguration involved. But sadly, there are also behaviors like the ductile one, which means the system comes back to a certain level, but its functionality is not completely restored. And of course, the worst case, we have the collapsing behavior, that the system is not able to recover and completely loses its functionality. So in this different types of behaviors, we can say that the robust and the adapted behaviors are more resilient than the ductile or the collapsing behaviors, since they either avoid the performance loss better, like less drawdown, or boost the bouncing back more, like quickly going up or just shorter recovery phase compared to the other two. So apart from the definition, it is also important to understand different dimensions in order to develop an appropriate approach to measuring and improving resilience. So in the research from Bruno again, they also developed 4 dimensions of resilience. And the first and most intuitive one would be the technical one, that involved more about the physical infrastructures we're looking at. So this determines the ability of the physical system to perform to an acceptable level when it's subject to a hazard event. But we cannot neglect other dimensions, for example, the organizational one. It describes the capacity of an organization to make decisions and take actions to plan, to manage, and to respond. And of course, the social and economic dimensions are always there. Sometimes they're a bit implicit, maybe can be reflected by the dimension from technical, but they need to be taken care of always. A more simplistic characterization was also provided from the US National Infrastructure Advisory Council. So they distinguishes between those practices related to people and process on the soft side, and those related to the structure and asset side, so the solid hard side. So as an engineer, it's always the technical resilience that we put most focus on, because it's easier to quantify, to measure, and is closest related to the physical infrastructures where we can model. But it is always vital that all the other resilience dimensions are given equal consideration, and especially within the critical infrastructure and lifeline sectors. So not only does these dimensions provide improved outcomes for the overall sector, but it also delivers like enhanced leadership, enhanced reputation, lower costs, increased innovation, and many other tangible benefits. So this is something I really want to bring up in the critical infrastructure resilience scope. So I just added this slide after the Q&A earlier regarding Jonas' talk. So someone asked about specific metrics towards the transportation system resilience. So here I would like to show you the other two commonly defined metrics that we've seen a lot in the classic transportation research. The first one is called reliability. And this concept actually focuses more on the probability aspect of risks because it is describing the transportation networks remain satisfactory under perturbations in terms of service level. And vulnerability focuses more on the consequence side of the risks. For example, we're talking about how bad the perturbations could cause to the system, focusing on both perturbations and also disruptions. And also, of course, we have the resilience. So how different are they? I'll use this chart figure from a recent paper published on transportation research to illustrate. As we can see that, so reliability is defining how often the system can stay above this green line, this required performance level. And it focuses more on the perturbations rather than disruptions, which means we are more looking at the disruptions happening day to day, more like disturbances. And the level of service, how likely the level of services can be maintained matters to us most. And while the vulnerability is describing the fall of happening after the resilience. So in this regard, we can say that vulnerability is not on the flip side of resilience, but more like a component of it. Because of course, lower vulnerability will contribute to higher resilience. And while higher reliability probably will result in lower resilience as well. So, but as we also can see that the high reliability does not necessarily lead to low vulnerability, as they are often considered different types of perturbations. So we can compare these two figures. They probably have the same level of reliability, but the vulnerability of this system is definitely higher compared to this one. So all in all, these concepts are applicable to different scenarios and provide information from different perspectives. So it is vital to choose the proper concepts and indices for evaluating the network performance under different levels of like disturbances, perturbations, or disruptions. So now I would like to know a bit about you, the audience, before we move on to the hazard talk. So here you can see a map of the globe colored differently. So I will let you know what the color refers to later. But now I would like to invite you, if you can key in this website, the address, and then you will see this figure in your browser. It works on your laptop, works on your phone. And I would like to indicate where you are at currently and the location. And and pay attention to the location you pinpoint. What color is it? Later on, we will come back to this. So now I start to see the pin dropping. We have someone from Southeast Asia, obviously. So wait. I'm sorry, since give me 1 minute. Okay, now we come back. So we have, oh, I was a bit surprised. I thought there would be more audience from Japan, but it seems we have a lot from the Philippines, from India, and even from South Africa, while from South America as well. So this is really impressive, quite a diverse audience. Okay, from North America. Okay, so I'm sorry, this is not a very high resolution map, but if possible, can you remember the color of the location you are dropping the pin at? So later on, we'll come back to that. So you see a lot of pin dropped in the area colored as lighter orange, and also a lot in the green. Okay, so now let's move on to the next poll. So as you probably have already guessed that these colors are representing different types of hazard. So the hazard here are referring to the dominant hazard that the transportation infrastructures are exposed in these areas. So we're talking about the roads and railway structures. So now I would like to invite you to answer what type of the hazard do you think is the light orange? So the bar I've placed here, so this color, what do you think, what type of hazard this is? And you can vote on the same poll. I think it already refreshes on your browser. So if you didn't participate in previous poll, you can again key in this address and key in your answer. Okay, we are seeing the results now. Surprisingly, most people vote for earthquakes. Okay, now the surface flooding is catching up. We need some drum beats. Okay. Okay, I guess this is the result. Okay, seems the poll is full. It's quite a great turnout today. Sorry for the limitation on the poll. So, okay, as the result, I see the majority vote for surface flooding for this one, and this is the correct answer. So now let's take a greater detailed look at these hazards. So this, due to the spatial distribution of transportation infrastructure, we can see many transport assets are exposed to natural hazards, increasing the cost for the national agencies' operations. So this is the figure from 2019, a publication from Nature Communications. They estimated the global hazard risk and exposed onto the road and railway infrastructure. So in this figure, we can see that the hazard causing the highest road and rail transport infrastructure there are many types. So we have earthquakes, cyclones. Cyclones here, we focus on the wind speed only, and also the surface flooding, also the pluvial flooding in other terms, river flooding, the fluvial flooding, and also coastal flooding. So we can see that the surface flooding and also the river flooding are the hazards causing the highest expected annual exposure levels in most countries and regions globally. It reaches almost 40% irrespectively and 30%. And also the tropical cyclones, the green areas, is the domain name hazard for the Eastern China, South Asia, as well as the Caribbean, and also the US Gulf and the East Coast. An earthquake, for instance, let's look at the earthquake. It was misleading previously. So we can see, for instance, the domain name hazard for earthquake, of course, is the San Andreas Fault and also the coastal line of Chile and Peru. And looking at this, I would say I feel very concerned, and given the current climate change, urbanization, and also the increasing dependence of our national and global economy on infrastructure systems, this will continue increasing the risks associated with the damage or disruptions to public and private assets. And now is only we're looking at the natural hazard only. And don't forget, there are also the man-made type of disasters. There are, even when we enter the next era of all the digital cyber physical system, there are also cyber attacks from all rounds. So it is crucial that the countries, when exposed to the hazards, they need to improve the transport planning by systematically including the risk information and improving the protection of their most vulnerable and critical assets. So since there is the need for better risk information to avoid spending money on all assets, but being able to spatially target improvements. So here I would like to share with you a research collaboration from our Singapore ETH Center, collaborated with the World Bank Group, in which we aim to demonstrate the significance of incorporating resilience thinking to public infrastructure planning by providing some tangible cases using disruptive technologies and promoting our urban-rural scape platform developed by the Future Cities Lab Global. So this is a very versatile platform. Later I will show you that can do the data fusion as well as analysis when we have different types of data, and assisted the urban planners to solve their problems. So since the disasters are not always preventable, we hope to provide certain insights on the identification of the hotspots or the bottlenecks under threats. And also, can we come up with certain contingency plans with these insights? How do we protect our lifelines when the city is under risks? And also, what can we do after identifying these hotspots? Can we do some structural measures for disaster risk reduction? So this will be answered in the later on use cases. So first, I would like to introduce how the digital flow is like in this project. So first, of course, in Ho Chi Minh City, we looked at the flood risk. And while the data availability is not the most ideal, we have received the Phantom flood maps from the World Bank Group and great support. So the flood hazard maps employ the hydrological modeling and providing probabilistic information in the sense of the return periods pertaining to flood depth. On the other hand, we've obtained the road transport network data from the OpenStreetMap. So this is not the best, but it's sufficient for us to carry out some crucial analysis on the crucial infrastructures. Then by overlaying the road network and the flood hazard map, we can do the exposure and disruption analysis to we made certain assumptions like how the road segments were disrupted given the risks of flooding, and how this road closure would impact the resultant traffic patterns. So last but not least, we will be deploying the topological analysis from the field of network science to identify the critical components in the road transportation network. So we gave the idea of what are the critical road segments you need to keep them in service, that your city do not suffer a bigger loss or damages in terms of services, in terms of throughputs. So first, the project I would like to show you is the BRT corridor planned in Ho Chi Minh City. So in this use case, I would like to demonstrate the capability of our Earthscape planning tool and how it can assist the planners to do a catchment area analysis. It's super easy to identify the beneficiary or the impacted communities just by clicking on the urban on the maps. And then another study that involves more closely related to resilience, that we look at the vulnerability and component level. So the Earthscape allows us to put the flood risk map together as well as the road network, and we can easily identify where the vulnerability lies in on the road networks. So now I will just play this a short video clip and hope see how the use cases can be done. But before the video starts, I would like to show you, this is the very neat and interface of Earthscape. So on the left-hand side, we have all the data layers imported in, classified into infrastructure, land use, and even the contextual data. Here we are looking at the flooding hazard. And then lower panel brings us a set of analysis tools that are very easy to use. So I'll play the video for you and you can show it. So I know it's paced a bit fast, but we can see there are a lot of we can do as long as we put the hazard data as well as the infrastructure data together, given this versatile digital planning tool. But currently, this tools only look at the components level. As we can see, it targets at either the stations or the road segments. But what kind of roles are they playing in the whole transportation network? So for this one, we need a more comprehensive network level analysis. So this is the second study I would like to share with you, that we looked at the emergency services supported by the road transportation network. So now we are no longer focusing on which road segment is inundated, not in service, but we look beyond that towards the whole network. So what are the consequences of something not in service? So here we identify their importance as the hotspots based on network science. So if a road is really crucial in supporting a lot of trips to a crucial destination on the disaster, we would never want it to be out of service. So that's the scenario behind it. And by specifying the entry and exit points of these crucial trips under emergency situations, we can identify the critical road segments accordingly based on the network science theories. For example, by using the location of a hospital as the single destination, node, and then the critical edges that ensure the travels to this critical location will be identified. And furthermore, we can take consideration of the social costs into the study by incorporating the human assets data if it's available. So now let's look at how this criticality was identified and how they look like. So this is a figure showing the road importance in a 10 minutes catchment network of the District 4 hospital. And this is under a normal situation, which means no surface flooding and every road is in service. And now we can see that the importance of roads in the catchment network, of course, is originating from the selected hospital, and a number of highly important roads constitute two prominent routes reaching the north. And in the enlarged plots here, we can notice that actually there is a bridge closest to the hospital is not highly used, surprisingly. And this is due to the fact that on the main roads nearby permits higher speeds. Crossing the bridge would require a U-turn in routing. So this simple analysis illustrates the importance of keeping the road attributes in greater detail, such as the length, the orientation, the speed limits, even in topological analysis, rather than simplify them to basic graphs. Otherwise, it would yield unreliable results. So this is a figure that after the flooding, so we are looking at the 20-year return period pluvial flooding, and we can see there are scattered flooded areas on the map already. And we have made the assumptions that the inundation depth, as long as it's deeper than 0.3 meters, we regard the road as not in service anymore, which means traffic cannot traverse through it, the road will be closed, and then people have to reroute towards the rest of the road network. So when we disrupt the network by the heavy flooding, we can see that the road segments and adjacent nodes were removed. So here, for example, and then we applied the metric on the importance again on the same area. And now let's compare this before and after for a better illustration. So we can see this is a plot of the comparison where the brown one is indicating the importance increase after the flooding, while the green one is the importance reduction. So after the flooding, there is this obvious shift in the concentration of roads with higher centralities towards the northern bridge, which provides an alternative to connect the eastern parts of the river with this hospital. And the main cause of this change is due to the inundation of the road connecting the second river tunnel. So this major connector was down. And so from a policy standpoint, these sections of road, these brown ones, they were not that important on a normal situation when we look at this emergency case, but their importance emerges immediately after the disaster. So this should inform the planners that to keep the functionality of these alternative crucial routes remaining parts of the system after the flooding will still be able to sustain a satisfactory level of service. So furthermore, to take more social aspects into consideration, such as the equity in terms of human assets, because people do not live homogeneously spreading over the urban areas, so we further associate the trips with population density and their origins, which means there could be a higher demand of the emergency trips towards the hospital. So this result here gives us a more realistic impression of how many people are affected by a potential network disruption, considering their distribution. We can see that the importance of routes reaching towards the northern part of the city overweighs the ones that reaching south previously. So such analysis can be of help when it comes to road protection or investments in a cost-benefit analysis scenario, such as further enhanced by the GDP maps, even if the data allows. So this is the two use cases I would like to show you today, and also it brings us to the summary of my presentation today. So first, as I emphasized a lot on the non-physical, the non-technical aspects of critical infrastructures, that the both social and economic aspects matters a lot. So improve the understanding of critical infrastructure factors, which may determine the criticality, not only from the physical side, but also the vulnerability might lie in the societal side that cannot be easily quantified or measured. And then the second point I would like to propose is that the system of system perspective, which is also an ongoing research in FRS and our Singapore ETH Center. So we are aiming to consider the complete range of hazards and the complex failure modes among the systems as a result of the interrelated upstream interdependencies. So the research questions will be placed in like, how do we quantify the uncertainties propagate from one system to another, and how long spatially and temporally such effects should take place, and should we allocate it to another system. So this is still the ongoing and very hot topic research in the field of resilience. And last but not least, I would like to pinpoint this, since we also have some audience from the public sector, I believe, that what concerns us most is always the money, the investment. Where do we place them? So this also deserves a further economic and also engineering research, that we need to find the favorable investments in resilience. So in this way, to better understand and quantify a suitable level of investments in technical resilience, should we place, because in the past research, it's been shown that the pre-disaster prevention investments is always more favorable in the cost-benefit ratios, as long as the investment for post-disaster recovery also matters. So how do we allocate the investments onto these different stages of disaster preparation and recovery is also worth thinking, and it definitely takes more efforts, not singly from economic side, but from jointly the engineering and also the economic fields. So this concludes my presentation today, and thank you very much for your attention. And I would like to turn to the question now.
Thank you so much, Dr. Wan, for your fascinating presentation. And thank you so much for showing us some sort of the modeling type of things, what you are doing. And yes, we have received a couple of questions. Okay, so first of all, how to decide the protection level of critical infrastructure?
How to decide protection level? So first of all, I think for critical infrastructures, lots of infrastructures, they have the building codes, and as a civil engineer, I believe like you follow a lot of design codes, performance-based design to build these structures. So I think when you talk about the protection level, it should have already embed a certain level of risk assessment in this design code already. So when you follow the code, you've already taken certain risk into consideration, but this is also what we've been advocating for, that most of the design code and the current stage would not take consideration as like the climate change, futuristic impact back onto the protection we are aiming at now. So I would say this is the minimal level of protection. And also, of course, when there are specific hazards identified for the areas, there definitely to be special attention to be put, especially like earthquakes for Japan, and also hurricanes for the coastal areas in the US and such. So I'm not I don't have much exposure from the planner side, like how to decide a protection level, but I think we all agree that never enough is enough. But I think for this aspect, we can definitely allocate like a grading or a scale where it works for first in the risk hedging as well as the cost analysis. So I would say so far, I haven't, as far as I know, I don't think there is such a grading for the protection level, but I think this is something maybe the planners should take initiative on towards the bigger protection of the longer climate change effects. So I hope this answers your question.
Okay, thank you so much. Okay, so the next question, in the context of the resilience graphs, how does one determine the required performance level? Is it based on site survey?
So I'll use transportation system as an example since I'm most familiar with. So usually in transportation system, what we looked at most is the total travel times, which means the delay basically of everyone experiencing, because money is time, and we usually calculate this time, convert it into monetary terms, then we can compare it with all the other sectors. So, but that is the very classic one in the transportation system, but sometimes delay doesn't reflect enough, especially when we look at different trip purposes. If you are going to work, or if this is a health emergency trip, it matters differently. So I would say for this network performance metric, it's very, very complex, and usually we should not target at a single metric. And we should be including like a group of indices that focusing on what I just mentioned, different dimensions from the physical infrastructure, the level of service, as well as the societal, as well as economic, as well as the organizational. So I would say different city, different countries, and even different systems, this performance level metric deserves a very comprehensive research and study. So I would not say, ideally it should be a group or a combination of performance indicators rather than a singular one.
Okay, all right, thank you. Okay, so the next question would be, have you considered using complex network theory to simulate the failure of critical infrastructure?
Thank you very much for this question. Actually, we already applied some, like I would say not deep complex network, but we've been using the metrics from topology analysis, such as edge betweenness, centrality betweenness. So using these metrics to give us, this provides a very computationally efficient way of analyzing different networks. But what it lacks is also the unique attributes associated with specific system. For example, transportation, we're not moving power or flows. we are moving people, and people have their own behavioral choice that sometimes the complex network cannot take off by simply looking at the road segments and assuming the particles would be transposed very optimizedly freely in the network. But I think this is a great direction to go further down, and there should be some integration of this complex network, which is both based on graph theory, based on topology, and combine it with the specific system-based, or we say the flow-based analysis. Because I do see the complex network theory has potential also for analyzing social networks, even power networks, and as well as water. I think this is a great direction to further continue working on. And yeah.
Okay. Yeah, thank you so much. Due to the limit of the time, I think the next one is the last, will be the last question. How often do you think risk assessment or resilient plan of infrastructure should be revisited to hedge against climate change, natural disaster? For example, Germany recent flood is case in point, it was unexpected.
Yeah, there is also something I want to mention up, since it's related to this question, that the difference between risk assessment and resilient assessment or resilient planning. I think risk assessment is rooted in abundant research already, decades of frameworks development. But I feel the biggest difference between this is risk assessment is trying to prepare us with something we can foresee, which means we know there is such a risk, and then we evaluate its probability of occurrence, and then we hedge against it. And when the cost is too high or too costly, like the black swan event, the planners may just decide, okay, it might not happen, or they just throw the money in and hedge against it. This is the very traditional risk assessment framework. But resilience, what resilience deals with is more like to deal with something not that expected. So in this regard, what I mean is even the black swan happens, there are a lot of other aspects that the resilience planning can help with. For example, the recovery phase and the organizational efforts, like the swoosh curve just goes back faster. This does not conflict with the risk assessment, but more like mediate or assisting it in another role. So for this question, I think I feel the climate change is, we are still working on that, convincing the planners that climate change is happening, and what you need to do from this point now on is to incorporate it into your planning already. I think revisiting is already a little bit late, but of course it's definitely worth being called for. But I don't. So I feel for this disaster, just as you mentioned, the one in Germany was totally unexpected, and it's already beyond the scope of the planning. Then I feel the planners should have also paid attention to the aspects of the organizational, the resourcefulness, and the speedy recovery or respondents side of this disaster hedging. I think in the ideal case, it should always be frankly revisited, but not always after a heavily heat system, but we always want to learn from our lessons. So I would say the best ideal case would be we keep a rolling horizon. And whenever there are new new insights or new implications that we can take the chance to incorporate it along the way to the future future planning and design.
Okay, thank you so much for answering all the questions. And again, I have to apologize, we could not take all the questions due to the limited time. So I hope Dr. Wan can probably answer the rest of the question later on through email or something like that. Okay, thank you so much again, especially for all the audience to joining us today. So that's all for today's session. I'd like to extend our sincere appreciation to Dr. Jonas and also Dr. Wan once again for their inspiring lectures. Also, our appreciation goes to the audience who joined us today. And I hope you enjoyed the session and learned from the excellent presentations given today.